Welcome to BTEC Revision. In today's lesson, we're looking at capacitance in series and parallel. By the end, we should be able to calculate the capacitance in series and parallel circuits. How do capacitors behave in parallel? Let's take a look at this circuit. We have a power supply at the top, the voltage V, and we have two capacitors placed in parallel. And what's going to happen is, once this circuit is set up, everything's working, we'll have a current flowing through the circuit, and the electrons going to be stored on the capacitors. The capacitors only have a certain set amount of area in which these electrons can be stored. Let's call this A. If you remember from last lesson, the equation for capacitance equals epsilon naught, epsilon r, which are constants, times the area of the capacitor divided by the distance between the two. So this is the equation that governs how much capacitance or amount of charge can be stored within the capacitor. So as you can see, it depends upon the area and the distance between the two plates. So as these electrons are coming along, let's look at the first capacitor. They go up and along and are stored on the first capacitor with an area of A. So they have a certain set amount of capacitance. And since there are two capacitors in parallel, the rest of the electrons are going to go down, go along, and be stored on another area of the capacitor, the second capacitor. So what this means is, in this case, the area has doubled. So looking at the equation, if we times the area by 2, since the epsilon naught, epsilon r are constants, and d is also a constant, therefore the only variable here is the capacitance, and therefore that will also double. So what this means is, to work out the total capacitance for capacitors in parallel, we can just sum each individual capacitance. So for example, in this case, we'll have total capacitance in this circuit, which is equal to C1 plus C2. And that's the total for the circuit here. In the case of bigger circuits, where we have more capacitors in parallel, we can just keep summing each capacitance of the capacitors until we reach the last capacitor. One more important thing to note here is epsilon r is dependent upon the material that we place inside the capacitors. Okay, so this is also known as the dielectric. So for example, this could be 1 for air, and another example would be 80 for water. Now, let's take a look at this example. Two capacitors C1 and C2 are connected in parallel. C1 has a capacitance of 12 microfarads and C2 has a capacitance of 18 microfarads. Calculate the total capacitance when they are connected in parallel. We'll start by writing down our equation. CT equals C1 plus C2. And we can stop there because there's only two. And we can just place these values in, 12 microfarads plus 18 microfarads. And since they're the same unit, I can add them up. So 12 plus 18 is 30, and that would be microfarads. Since we put in micro into our equation, and all these other values are micro, we can add this up. And our answer is going to be micro as well. The answer is 30 microfarads. How do capacitors behave in series? Looking at this circuit, we have a voltage V and two capacitors C1 and C2 in series with a current flowing through the circuit. Focusing in on those capacitors, if we have electrons flowing through, they are going to be stored on the sides of the plates. Looking at the first capacitor, we can work out the capacitance via our equation. C equals epsilon naught, epsilon r, A divided by D, which is the distance between the two plates. And as you can see, for the first one, C1, the distance is D. The electrons are away from the other side, the positive side, with a distance of D. However, for the second capacitor, C2, the electrons are again distance D away from the other side of the plate. So there are two distances here. They are away double the distance. So looking at the equation, we can times that by 2. And since capacitance is inversely proportional, we have to the distance, we have to divide capacitance by 2 to balance out the equation. So in this case, the capacitance is going to decrease. If we had a third plate in series, then we'll have 3 times the distance, and therefore we'll have to divide capacitance by 3. And this can be simplified with this equation here, which is 1 over CT. CT stands for the capacitance, total capacitance, and that's equal to 1 over C1 plus 1 over C2 plus so on until we reach the last capacitor. So for our case, we have 2 capacitors, so we can write our equation like so. So 1 over CT equals 1 over C1 plus 1 over C2. Let's take the case where C1 is equal to C2. Right, we have a capacitance of C, so we can just drop that out and we can simplify this, which gives us value of 2 over C. And if we take the inverse on both sides, that gives us CT equals capacitance over 2. And that's the same as we just worked out over here. Now, let's take a look at this example. 2 capacitors C1 and C2 are connected in series. C1 has a capacitance of 15 microfarads and C2 has a capacitance of 20 microfarads. Calculate the total capacitance when they are connected in series. We'll start by writing down our equation. Since we know it's in series, we'll use the series capacitance equation here. 1 over CT equals 1 over C1 plus 1 over C2. And we know there's only 2 capacitors, so we don't have to carry on. We plug in our values. 1 over 15 plus 1 over 20. Okay, which gives us a value of 7 over 60. Now we can just take the reciprocal on both sides, which gives us C total equals 6 over 60 over 7. And this gives us a value of 8.57. And the unit, since we plugged in our values with the prefix micro, our final answer is going to be in micro as well. So that's going to be 8.57 microfarads. Now pause the video here and attempt this exam question. A circuit with the following combination of capacitors with equal capacitance are connected as shown below. What is the total capacitance of the circuit? We can start by labeling our capacitors, the value of C, and we can work out the capacitance in each individual section here. So looking at capacitors in parallel, that's probably the easiest to start off with. So this section over here, we can just add them up. And we can therefore redraw the circuit, okay? Because they're in parallel, they'll add up. So let's redraw the circuit like so. So we'll have this capacitor in series with this one, which is the same as if we replaced this with the capacitance of 2C, because we know capacitors in parallel just add up. Okay, so that C total here is equal to C1 plus C2. In this case, they're the same. C plus C, so that's just 2C. So we can just redraw the circuit like so. Okay, and then we can see here we've got one more capacitor, like so. And these are in parallel as well. So we can just add these up and we can redraw the circuit again. So that would give us capacitor C, and then these two add up. So that's an even bigger capacitor. We can replace to give us the same result. Okay, and now we can use our capacitance equation for series, which is 1 over C total equals 1 over C plus 1 over 3C. And we can manipulate this, so that will give us 3 over 3 there. So we want to make the denominators the same, so we can add these fractions, which gives us 4 over 3C. And now we can take the reciprocal. So that gives us the value CT equals 3C over 4. And that's the end of the lesson. If you'd like to boost your grades, visit us at btechrevision.com, where you can try the quiz questions and there's lots more resources. See you next lesson.